Okay, so let's start today's class. So today we will finish the difference design, and then we will introduce another identification strategy called synthetic control method. And then I will briefly explain the homework 2. Or I might record a video. If we cannot finish this, I will record a video to let you know how to do your homework 2. But basically, the homework 2 is related to the second part of data. So I just upload the video for the data, like how to create a sample for analysis. And so the homework 2 will just ask you to practice this command and also some graphical visualized data, the command for using this data. So you can just watch the video. Okay. And then we will start to introduce how to use R. But I will also record a video to let you know how to do that. And your homework 3 will use R to finish it. Okay. So any questions for this? Okay. Okay, so last time we give you some basic idea to let you know how to implement the difference design. So today I would like to let you know how to examine the common trend assumption, which is very crucial for the difference design. So the key assumption of the difference design is the common trend assumption. That is, in absence of the treatment group and control groups, their outcomes trend need to be parallel, have very similar trend. Okay. And so you need to test this, whether this common trend assumption is satisfied or not. If it is satisfied, you can use different design to estimate the causal effect. But if not, your result might have some problem. Okay. So we can use pre-treatment data to show the trend are the same, because before the treatment happened, both treatment group and control group does not have received any treatment. So this satisfy this condition in absence of the treatment. So you can just look at the outcomes trend before treatment happened for the treatment group and control groups to see whether they have very similar trend or not, to verify this assumption. Okay. So for example, you can just draw the graph trying to understand the outcome for the treatment group is the blue line, and outcome for the control group, the green line. And the red line means the date of the treatment happened, the treatment year. And from this graph, from you use I, you should find actually before treatment happened, these two groups of people, their outcome looks similar, have similar trend. That means they need to have the same outcome, the same level of outcome. They just need to have the same trend is enough. And after treatment happens, the trends start to become different. Okay. And these graphs show that their trend actually are not very similar before treatment happened. So in that case, maybe you should not use different design. Okay. But you can formally to examine this. Okay, using the regression, using the when you can include the leads and lag term in the difference design to examine the common trend assumption. And I will let you know how to do this practically in practice. So it's also called the difference event study design. So it studies some event happen. How does the trend between treatment group and control group change after this event? Okay, so that's so-called event study design. So in this design, you will instead of have the post dummy, the dummy indicate the post treatment period, before or after treatment happened. This dummy. Instead of this dummy, you will replace with this new dummy called ET. This is the dummy variable, a set of dummy variable indicating the individual eye is observed at time t, at year t, year 1, year 2, year 3. So usually we will recenter the timing to the treatment, the time for the treatment happen. So treatment occurs in the time 0. Usually we will say that. And we usually use the time just before treatment happened as the reference time. So it's like baseline difference between the treatment group and control group for their outcome. So okay, you can consider that. We usually use the time minus 1 as the reference time. So E minus 1, this is the dummy variable indicating, for example, just 1 year before treatment happened. Okay. So we will create a lot of dummy variable indicating this timing. The year after the treatment happened, 1 year after the treatment happened, 2 years after the treatment happened, 3 years after the treatment happened, until Q year, for example. And N year before, if this is minus, means before. 1 year before treatment happened, 2 years before, 3 years before. And we usually will use the 1 year right before the treatment happened as the baseline year. So the minus 1, the t equal to minus 1, this dummy, we will not include in our regression. It's the reference year, reference timing, okay? Because if you include that, they will have collinear problem. One must be dropout, okay? So usually we'll use this as a reference time. So every year, the outcome difference between the treatment group and control group is compared with the year just before treatment occurs, compared with the reference year's difference, okay? So we will use this, a set of dummy variable to replace the post dummy that we just discussed last time, okay? And the key variable is the D treatment variable, treatment group, the dummy for the treatment group interact with this event time dummy. The E is called event time dummy, their interaction. And this interaction is represent the difference in the outcome between the treatment group and control group. This difference in each event, each timing, compared with the reference time. Okay, and we want to see whether this difference in outcome between treatment group and control group, they become bigger or smaller after treatment happened, compared with the difference at the reference timing. Okay, so if we find the difference in outcome between treatment group and control group become very different compared with the difference at the reference timing, that means treatment might have some effect on your outcome. Okay. So that will represent by this its coefficient gamma 0, gamma 1 to gamma q. So we can measure each year's impact on the outcome of the treatment on the outcome. And also, we also want to examine before treatment happened, this difference between the treatment group and control group should be very similar to the reference time. Because before treatment happened, it shouldn't have the difference between the treatment group and control group. This difference should be constant because they have the same trend. So like this, they are constant over time. Become constant over time. Compare with the reference year. For example, we usually use the year just before the treatment happened. So this difference will always the same. So we will expect this coefficient. So this will measure such coefficient before the treatment happen, and should be 0 or very close to 0. That means the difference in outcome between treatment group and control group, these differences are very similar to the difference at the reference time. Okay. So I will use this example, my paper's example, to know what does this mean. Okay. So any question for this? So this paper is about whether do people have children when they become rich. So we want to know the causal effect of the household financial resources on the people's fertility decision. So that means whether if you have more money, if you have become rich, whether you will have give more children, give more births. Okay. And we use the lottery winners in Taiwan as who win the big lottery prize as the exogenous change in their household income as a nature experiment to examine this issue. And we use the different design. So the motivation of this paper is, you can imagine during the past 15 years, the fertility rate, especially in developed countries, they declined dramatically. Like Taiwan, our fertility rate, like the total fertility rate per woman could be 6 children per woman during their lifetime. And until now, it's below 1. So actually, it creates a lot of problems like aging population and the workforce shortage, because we don't have enough adults in the future to support our working workforce. And also, it will also reduce the tax revenue for the government. Okay, so many countries try to initiate the children-related cash transfer policy, try to encourage childbearing, try to encourage people to give more births. And on average, for OECD country, such public spending for the children can account for 1.1% of the GDP. So around 1% GDP are put in to stimulate people to give more births. And the rationale behind such policy is the children actually has positive externality. So that's why the government need to subsidize. If the children not only support or give the utility for the parents, but also might support government's tax revenue or increase the economic growth. So that might also benefit to the people who do not have any children. So government might want to do this, implement such policy to give more money for those who have the children. Okay. But empirically, it's hard to understand the relationship between the household income and fertility, because we usually use the wage income as a proxy for the household income. And if we use the wage income as a proxy for the household income, because most household, their income source is from their wage, their salary. But if we use that as the income to estimate the effect of the income on fertility, we usually get a negative relationship between the income and fertility. So higher income people actually tend to have lower fertility. Okay, and this is not because the income effect is negative. Okay, it could be other reason. For example, the reverse causality. So it's because the arrival of the baby actually reduce household income. So many study this issue by looking at the child, they call child penalty. So that is, they find the woman, if they have the baby, when they give a birth, their wage income will reduce for over 10 years, because they might give up their career, they might not have job after they having the children. they leave the labor market. Okay, so this is the fertility affects your income. Now the income affect the fertility. Okay, so you might have this reverse causality problem. And more important is the income effect might confound with substitution effect. If you use the wage income as an income source, that might have this problem. Because both working and raising children are time consuming. And everyone just have 24 hours. If you work, you cannot have the children. And if you have children, it's also hard to find the time to work. Okay, so they kind of like substitute. So this substitution effect might confound with the income effect. So for example, a sudden increase in wage income will increase the opportunity cost of having children. So it's increase the relative price of having children. So the cost of having children will increase. You might reduce the demand for the children. So typically, if you find the wage income increase, the fertility rate will decline. But it's not means the pure income effect is negative. It's just because the substitution effect is too big. It's bigger than the income effect. Okay, so ideally you should need to find the income effect which is unrelated to your working. Okay, so some income change is due to some exogenous variation. So in this paper we look at the impact of large and permanent income shock induced by winning the lottery prize. So whether you win a lottery or not is due to the luck, not just because you earn more, you win the lottery prize. So this arguably is unrelated with your working condition or working status. And then you can eliminate the substitution effects and also can avoid the reverse causality. Okay. So we use the difference design to examine the causal effect of large income shock on fertility. So we compare the trend in fertility before and after receiving the large windfall gain between the treatment group and control group. And the treatment group is the household who win more than 1 million NT dollars from the lottery prize. And the control group is household win less than 10,000 NT dollars. So the one win a very big prize from the like 统一发票 or 公益彩券, the Taiwan received lottery or public welfare lottery. And one just unlock, they never win such major prize. So who win the major prize or not is arguably random. It's random. So we can use this variation to generate the causal effect of income on the fertility. Okay. So the different design, the regression is like the following. We want to know how does this income affect on each year after they give in the birth, after they winning a lottery prize. Okay, and also we want to test the pre-trend before treatment happen, whether the treatment group and control group have a similar trend. So we follow this group of people, the treatment group and control group, the same household over time, from 3 years before treatment happened, from 3 years before they winning a lottery prize, until six years after they winning a lottery prize. So follow them for over like 10 years. Okay. So okay. 一方面是看你的样本有多长，如果你样本很长，你可以取得很久，也可以看10年后。那我们就是，然后就是 一方面是样本长，但如果你样本要拉得很长，就是你要追一个人追好几年，你就没办法用很多中奖的人，因为他是中奖后10年，所以如果你拉得越长，你可以用的中奖的那个人的数量就越少，因为就越少人可以看到那么久，对，所以就大概有2个 trade off， 你看得久，但是你看的人数变少。还是看的人数变多，但看得短，对。100万，这个倒没有特别决定，但是就是要够大，然后挑一个整数这样，对。但我们也有看500万以上，基本上效果是，如果你是中100万到500万之间，是不会对你的声誉有任何影响，要中再更大一点才会有影响 ，OK。
可是 income 的性质会有点跟一般想象的wedge其实本质上就差异很大。
对，但这个正是为什么要这样子做的原因，因为如果用 wage 的话，就会有这个 substitution effect， 你摆脱不掉，因为我们目标是要估纯粹的 income， 就纯粹是因为你钱变多，但是如果你 wage 改变，除了钱变多之外，也会影响到养小孩的 opportunity cost。因为工作的就是 wage income 工资，这个是你一定要花时间工作才得得到的 income， 那它会产生这个替代效果，因为养小孩跟工作都需要时间。但是我们这边看的 income 是，我们这边这种 income 是平白无故得到的，他根本没花时间就突然有上百万中了。所以它的效果就是纯粹是 income。So any questions? Okay. So the treatment group dummy is a D. So as I said before, if household win more than $1 million in a given year, they just win in a specific year. And we exclude the people who win multiple times. And actually, not a lot of people are so lucky can win the $1 million over more than $1 million over time. And this, on average, this household win more than 17 million NT dollars, 1,700万. So they actually receive very, very large income flow. Okay. So you can consider this kind of like permanent income change. Actually, over their lifetime, they can just earn such amount only. Okay. And control group is just earn less than 10,000 NT dollars. So over the sample periods, they only earn that every year they win just below to the 10,000 NT dollars. Okay. So ensure control group does not receive any big lottery prize. Okay. OK， 好问。treatment group 大概1200人 ，1000。因为合并好几年，然后这是母体的资料，全部的中奖都在里面。So why we have this data is because the lottery prize is taxable. They need to pay 20% of tax. So it's not they separate taxing, not including your household income to the tax. Otherwise, sometimes you will need to tax 45 if you win the lottery prize. So that's why they have separate tax on the lottery income. So that's why the government has this information. Okay. No. Control group 就是所有符合这个条件的人，大概50几万。
这样不会差超级多没关系。
以这种比赛来说，控制组多一点人是不错的，比较好。就是像后来就会做一些 robust check， 也用 matching 让这两个更像，这两组人更像。
是说从50万元再挑出更像？
对，就只挑出1200人去跟他 match。
哦，所以说 control group 上有50万人，真的会使用其实有1000。
哦，没有，那个是做一个 robustness check。
哦，
我们做了一个 propensity matching， 做这个，但是没有做 matching， 我们主结果是没有做 matching 的，就是直接用这50万人去弄，因为他们其实本来就很像，可是他们中间还有一些特性，不知道为什么不太像，主要只有一个不太像，就是年龄。treatment group 比较老一点，老大概0.8岁左右，但我们也不知道为什么比较老的人比较会中奖。但他们是显著的有差，所以才会做一个 matching， 让他们在中奖前的年纪是几乎是一样的。这只是 additional 做的 robustness check， 结果都差不多了。
为什么人数差都不会有影响？
不会有影响。
应该说没有关系。
对，是没有什么关系啊。对，就是你觉得会有什么影响？有可能有影响，我可能没想到。
其实就觉得应该要找一样多的人来比。
没有，可是他们平均来说，这50万人的平均特性跟他其实都像。对。So any other questions? Okay. So we will estimate the following regression. The outcome is because we want to know the total effect of the income on fertility. So our outcome is a cumulative number of children for the household I in year T. So that means, for example, this year you have 1 children, and next year you give 1 more. So the cumulative number of children for the next year is 2. So it's cumulative number, okay? So then we will examine this until the 6th year after winning the lottery prize. So the key variable is this event time variable. As I said before, this ET is the dummy variable for the year, for each year. And the timing concept in event time is reference year. The reference year, we recenter all the year to the winning year. So 0 means the lottery winning year. So -2 means 2 years before winning year. -3 is 3 years before winning year. And also we create a dummy for the 1 year after winning year, 2 years after winning year, until 6 year. Okay. So ET is represent represent a dummy, a set of dummy for each year. So each year we will create a dummy. So instead of the traditional difference just post, before and after treatment happen, we create the dummy for each post-treatment period and pre-treatment period for each timing, for each year. Okay. And the key variable, as I said before, is the treatment group dummy times the event time dummy. So these measure the difference in the outcome between treatment group and control group in each year, compare with the reference year, the year right before the lottery winning year. And the reference year, the baseline year, you can choose -2 or -3. It doesn't matter, but you just need to choose the year before treatment happened. And you should expect the gamma. You want to focus on the gamma, this coefficient. And you will expect the gamma -3, gamma -2, such should be around 0. Because if they have common trend, the difference in outcome between treatment group and control group, for the year before treatment happened, this difference should be very similar to the baseline year. Should be very similar to baseline year. So should not significant from that year. And you will also expect the gamma 1, gamma 2 to gamma 6 will bigger or smaller than 0. It's significant from 0 if the receiving the big lottery prize has impact on fertility. Okay. So before looking at the regression estimate for the gamma, we can directly look at the the graph. Usually, for difference, it's very helpful. You can display the graph for the raw data to show the time trend in the outcome for the treatment group and control group. So the Y is the cumulative number of children ever born over time. So blue line is treatment group, red line is control group, and 0 means the lottery winning years. So minus is the before and positive is after. And you can see before the treatment happened, the treatment group and control group, their time trend are very similar. So that means they have some difference in terms of the number of children they have. But these differences are very similar over time before treatment happened. So that's why I say compare with the reference year's difference. These two differences should be insignificant from this difference. Okay, so that's why the gamma should be close to a 0, because we will compare with this difference is to a 0. Okay, and after the treatment happened, you can see the treatment group, their number of children slightly increase a bit. The gap becomes bigger, and you can see usually we will subtract the baseline difference to let you see more this pattern more obviously. So usually we will use the year just before the reference year, make they become 0. So their difference is kind of like baseline difference. So other difference is compared with this difference. So from this, so that means every data point in each year is just minus the number in the t minus 1. And you can see the treatment group and control group, before treatment happened, they actually have very similar trend. And right after treatment happened, the treatment group steadily increase until the 6th year. Okay. So this gap is continue until the 6th year after the winning the lottery prize, or 7 years. But due to the data limitation, we only can look at the 6th year. But we argue looking at the 6th year is okay, because average age when they win a lottery prize is 33. So it means these 33, 34, 35, 36, 37, 38, 39. So it's kind of like they complete their fertility rate, because over the 40 for the women it's hard to give a birth. Okay. So the coefficient for the gamma here basically is try to measure the difference. This difference compared with the reference year's difference. So this is the coefficient of the gamma. And you can see before treatment happened, this is very close to a 0. That means before treatment happened, the treatment group and control groups, their outcomes difference are very similar to the baseline difference. And after treatment happened, become positive. That means the income effect is positive. So, and also one thing I would like to just remind you is the effect for the year, the winning year is 0. It makes sense because you need 10 months or around 1 year to give the birth for the pregnant. So right after winning the lottery, 1 year after winning the lottery, the number of children start become significant positive. Okay. So our result basically suggests winning more than 1 million NT dollars will increase the number of children by 0.06. So it's not very big. So that means the result you can interpret like among 100 households, winning the lottery prize over 1 million NT dollars, only 6 households will give a birth. So our result basically suggests income do affect the fertility, but maybe it's not the major cause of the fertility decisions. So so I think it makes sense because usually the poor people actually give more births. So that means the substitution effect is more important compared with the income effect. Okay, so that means time is more important. Raising children, you don't just give them money. Giving them money, they cannot really increase their fertility. Give them more time is more important. Okay, that's basically, it's kind of like our implication of our result. Okay, so any questions? Okay, so let's example to let you know how to examine the common trend assumption, and also it's also useful. You can use the difference event study design to display your result, because you can show your result over time, the effect over time, not just before and after treatment happened. Okay. But it's also easier to summarize the result using the simple difference before and after, because you can just give the number to know the average effect on the outcome over the post-treatment period. Okay. So another way to test the common trend assumption, as I just said in the last lecture, you can use the pre-treatment data. You can just use pre-treatment data and arbitrarily choosing the treatment timing in the pre-treatment period. Okay, like the EITC example. The EITC expansion happened in 1994, but you just use the data before 1994 and then choose 1992 as the treatment period. A treatment happened, the timing for the treatment happened, but actually nothing happened at that time. And you run the very similar difference estimation, but you might expect this estimate is not significantly different from 0. So that means before treatment happened, the difference in outcome between treatment group and control group, they are all very similar over time. Okay. So that's another way to test the common trend assumption. Okay. So any question for this? Okay. So there's some issues about the difference when you do the difference design. One important issue is the change in sample composition. And this is especially true if we use the repeat cross-sectional data to implement the difference design. Okay. So in the difference design, you don't need to follow the same individual or the same firm or the same household over time. But it's good you can do that. But sometimes your data is repeat cross-sectional data. That means every year they randomly choose some individual into the sample. So they do not follow the same firm or the same individual over time. But in that case, you still can use the difference design, because we just need to require you can observe the treatment group and control groups over time. So they are not necessarily has to be the same person, the same individuals. They just need to has the same property, the same feature that can make you can define they are belong to the treatment group and some people are belong to the control group. Okay. But if you use this type of data, the sample composition might change. If you use the panel data, the sample composition might not change because you follow the same person. So you don't have such issue. But if you use repeat cross-sectional data, it's possible your treatment group and control group, their sample property, the sample composition might change. And for example, some policy reform might induce migration. So for example, the Taipei city just raised their tax rate on the housing, and that might make a lot of, maybe for poor people might migrate to New Taipei City. So maybe you want to use New Taipei City as the control group, but actually the New Taipei City also affected by this policy due to the migration, and also it will change the composition of the household between the treatment group and control group, because now the poor people might migrate to the control city. So in that case, that might also confound, this might bias the estimate of your causal effect, because the causal effect you estimate is not just the policy of impact, but also the effect due to the migration or due to the composition change in the treatment group, between the treatment group and control group. Okay. So you can verify this. You just replace your outcome as your covariate as the outcome to conduct the difference estimation using the covariance outcomes. And for example, as I just mentioned, the household income or household wealth might change due to this policy, because a lot of poor people migrate to control city. So you can use the household wealth as the outcome and run the same difference estimation. But you want to see there's no effect of your difference estimator. The treatment group dummy times post dummy, this coefficient is not significant different from 0. And if that means this covariance does not have significant change after the policy implement, after treatment happened. Okay, so that's one way to test it. Okay, so if your data is not the panel data, maybe you need to care about this issue. Okay, so any questions for this? So for my study here, we don't have this issue because we follow the same person, the same household over time. So they are the same person, the same, no change. But maybe in some situation, it's the repeat. If you repeat cross-sectional data, the composition might change. Okay. Okay. And one last thing for the difference estimation is when you do the hypothesis testing, the statistical inference. That is about the standard error for your estimate effect. The problem here is usually when we calculate the standard error of your coefficient, because for example, in this study, we usually focus on the coefficient here. And usually we assume our data set is IID. That means identical independence distribution. So that means this sample and that sample, has no relationship. This individual and another individual, they don't have any relationship. When we calculate the standard error of our estimate, we assume our sample is IID. So in that case, the standard error usually will become very small. But the difference estimate, usually we just focus on the group level. Or you are a treatment group and these are control group. Or you belong to that state or other state. And within the state or within the group, the individual might have some relationship. Okay, so this relationship will violate the assumption of the IID for the sample distribution. So that means you need to consider this correlation. And also, we usually will follow the same group of people over time. So this will make the year 1 and year 2, their sample might have some correlation, have some serial correlation. You also need to control this. So in this case, that means the standard error, when you calculate standard error, you cannot use the traditional standard error calculation. That is, you need to cluster your standard error at some group level. Okay, so depends on the policy variation happen in what kind of group. Some policy variation might happen in the city level. You need to cluster your standard error at some city instead of using the assume all the individuals are from the same distribution and from the same identical distribution. So simply solution is when you do the difference, you just change your standard error calculation using the clustering standard error. So you just type the CL and put the group level ID. So sometimes the policy might happen at the state level. You may cluster at the state. And for example, if some policy happen in city, you just cluster at city level. Okay. And there are other solutions I will not mention in this class, like using the block bootstrapping or white bootstrapping also can help you to calculate such standard errors. But they are all very similar. Just calculate some clustering standard error based on some level, group level. Okay. And usually, if you do that, your standard error will become larger. That means you will not your statistical significance will become less statistical significant because standard usually will become larger. That means if you do not do that, sometimes you might over-reject the null hypothesis. It's actually not significantly different from zero, but you find it's significantly different from zero if you do not do that. So usually now we realize there's such problem, you should try to care about what kind of clustering level you should do when you calculate the standard errors. Okay. So any questions? 对，这个是蛮困难的问题，就是其实目前没有明确的 guideline 说要 cluster 在哪边，但是通常你可能就是要看你这个，譬如说我们最关心的是，其实我们关心的是这个系数，这个变数的系数的假设检定，就是它的这个 inference， 就它到底是不是显著异于零还是不是？那因为这两个变数其实都不是在这两个变数其实是 group level 的，所以才会有这个问题。但是我们资料又是用个体资料在估，就是说它并不是它这里有变数的变异不是每一个人都不一样，而是只要同一个 group 的，它就会有一样的数字，所以这个 correlation 我们必须把它考虑进去。所以主要就是看你用的这个变异的这个变数，它的变异来源是来自于哪边。所以像一般如果是有些美国的研究，它可能是某一州有实施政策，另外一些州就没有实施，它的变异来源就来自于州。那虽然它用的资料是个体资料，可是实际上等于是同一州的人，通通都会有受到这个州的某些政策全部的影响，所以同一州人都有关系。所以他在算 standard error 的时候，他就是 cluster 在 state， 像这样子。那或者是他还会考虑一种是每一个 group 跟他们之间的 serial correlation。你也可以说你 cluster 是为了解决这个问题，就是今天的这一群人跟明天的这一群人，他们之间有一些关联。所以如果你是譬如说像我这一篇文章，我们是追踪同一个家户 over time， 所以这个家户的今天这个家户一跟明天那个家户一，他们之间是有关系的，因为他们同一个家户。所以像我们这个文就就是 cluster 在家户的层级。 那至于要 cluster 在什么层级，就是说得通就好。但是几乎不会有人再让你不 cluster， 就是你不可能直接用一般的 robust 的 standard error 去跑这种回归，你可能至少要讲一个理由，说我要 cluster 在哪边。Any questions? Okay, if not, just let you know there's some reference the suggestive readings. So chapter 5 for most harmless, or chapter 9 causal inference. If you want to know more about the different design, you can read this textbook. So next class I will go to the discuss the synthetic control method. So we can have the break.
因为这两题其实我都可以当做 baseline，
可是他这一题已经拿到钱了，
他来不及反应。
你这样说也对啦，但是我们通常不会把0这一期，就是它treatment发生的一期当做 baseline。哦，一个原因是除了这个，其他的 outcome 当期就会反应。这个 fertility 确实是一个比较特别的。譬如说他会不会做别的某些事情，股票投资可能当期就会反应。比如说我要看你中奖，对。
所以我目前只是看 fertility 这个。
对你对，所以统一通常都是一定会挑这个事件发生前的当baseline，去比较好。因为在这个之前，实验组跟标准还两组都没有被影响。对，所以他们两组的差异应该都会维持恒定。对，这个系数就是在比说这两期的差异，这个差异跟这一期的差异其实维持是一样多的。对。
这两期什么意思？
就是它这个系数都是在比这个 gap。上下上对。对，它其实都是在比，对这个 gap。然后我们都是以负1期当做基准的 gap， 也就是负1期的 gap 不是 gap， 就是一个基准。那等于是这个意思，等于是这两期的负2期跟负3期的 gap 跟几乎没有，对，也是几乎跟负1期一样大。其实这个就是从上面演化下来的，就是说他们这两期的 gap 跟第一期都很像。
所以下面那个其实是我拿这个的 difference 去减这个的 difference。我把这一段减到这一段等于这边的这个。
对，你可以这样想。那其他段跟它减，它都会明显比较大。在后面。那这边是这样子，就是表示有 common trend， 因为它们非常接近某一段，这一段就是 treatment 前的这一段。每一期都很像，表它们维持的是恒定的变化。恒定的差异。没有变化。
老师刚提到说，就是我们其实要去辨别说这个到底有没有是显著不等于0。可是我有点难想，就是因为我的理解是做 hypothesis test 的时候，其实是要去我们假设是这样说吗？跟母体去做比较。可是这个所谓的母体的概念，就是说
我懂你意思，这是好问题。这个我也不太清楚要怎么回答。对，确实我们用的都是母体的。那为什么还要再做 hypothesis testing？ 这个我也不知道。应该说，你如果关心的是台湾全体的话，确实不用再做，因为这个是母体。
其实我不是说不用，可是我在想的是说，就是如果说好，假设我再去测这个，我再针对这个怎么讲？有点像说这一群人是我的某一个 sample 嘛，1200人，我从母体里面抽出来，这样讲嘛，然后反正我抽这个人，然后我估出一个 gap， 那
没有，其实没有抽，我全用，
没有抽，
全用。 因为这是人体资料没错，所以确实有个问题，就是说到底做hypothesizing在这里是什么意义？
哦，懂意思。
我只能说这个只是台湾的母体，不是全。如果你是关注全世界、全人类的话，它可能是一部分而已。
哦，因为这一起
但如果你关键母体是只有台湾的话，其实不用再做 hypothesizing， 因为这个就是全部的母体，全部的人。所以这个 difference 就是真的有这个差异，因为我们并不是从2300万人再去抽个多少人，
因为那1200人就是全部人
所有中奖的人。
我刚刚其实会想问那个 income 的问题，因为我记得好像在上总监的时候，其实老师就提到说所谓的 permanent income， 就我们对于那个所得的增加，其实会有不同的反应。
对，
就如果是一次性的，它的反应跟我就是例如说都是1700万。那一种是每个月给你，或者是一次给你，
会有差。
那我总觉得，
但是它更大的差别，总经上更大会讲是不是预期还是非预期 ，expected 还是 unexpected。如果是预期，你就早就知道了。譬如说公务员年金改革，早就知道了，所以你不会真的到退休的时候才突然改变你的你是在你知道的当下。你就会做调整，就年轻的公教人员在年轻的时候就会做调整，他不会等到他真的领的时候才改变他的储蓄行为。那 unexpected 的话，他在那个 shock 发生的当下，他才会改变，才会有像这个就是 unexpected，因为他根本不知道他事情会有大的终结。就如果他是 expected， 他不会等到真的钱拿到他才发生事情，他这边就会没有 pretrain 的这个，所以说年改的效果不会是看他这个人到60岁的时候才会提升，他可能30岁的那个公教人他就会改变，对，他不用真的等到他领到一个已经减少很多的退休金才行为。
那这样说会不会有点像说，就是我们可能把很多期都当作是我们预期人类知道之后某一个时间点会发生反应，然后我们去做很多次这个，那怎么讲？我把哪一年当作是这个地名期的时候，你会有显著的变化，然后去断定说你在那个时间点会发生效果，会这样去。
你是说为什么这样所以你是说这个为什么要做害怕？
不，这是下一个问题。我刚只是听老师在讲说，我想下一个就是说，刚刚那个概念像说，我们预期人类会事先反应，
对，
但我们可能不知道它到底是半年前反应，就是我知道之后什么时候开始反应。
对啊，这个如果那个 income 的变化是 unexpected， 是 expected 的话，就是你事前已经知道5年后会有个变化。那你不会等到5年后才会改变想法，对你可能最近就会改变，经纪人就会这样子预测。
所以我刚刚孙老师意思就是像说，那我不知道到底是1年、2年、3年、4年，还是真的到5年。那如果我都把第1年或是第2年都当做这个，然后我去测看画出一个 trend， 那如果假设我知道第3年的时候发生明显的 trend，
可以啊，
然后就说那应该是在这1年发生行为的改变。
对，可能要这样反推，因为你确实不知道什么时候会发生。但是应该说，他只要知道资讯之后，他就有可能会开始反推。
对，
所以基本上就是经济学上会认为，事实是什么其实可能不是很重要，但是那个到底知不知道很重要。知道了他就会改变，但如果他一直都不知道，实际上有发生年改，没有人知道，那他也会行为不会改变。
了解。
但至于他什么时候行为才会开始变化，就不知道，就是他就是要，可能是要，但一定是他得到那个资讯之后才会发生。
正好是我作业，因为那个我都还没有coding完，所以我就拿了别人资料来做。
没关系，但是就趁机让你可以开始。
所以其实能开始就比较好。
对。
但是我后来查大概400多笔，我真的是没什么时间慢慢 coding 这样。
你现在怎么 coding？
我现在就是我挑选几个变数，然后就是人工阅读。
OK。
就是说赔偿金额，然后可能它发生的行为，然后可能就是评语有很多次， 其实我大概就是去阅读它，然后把它慢慢做编码这样。
了解。
可是其实我会蛮担心，就是我会不会编码了之后才发现我可能漏掉了什么，那会不会到最后要再重新编？我现在比较担心这个事情。
你那个判决书有些怎么写？可以出来吗？
它其实是挂在网上，所以我其实就是慢慢去读。但是400多，我觉得可能人工是比较好，因为我去问过，他们说其实你为了这个再去做文字上面，其实效率比较低，对啊，所以就
你可以 coding 到某个程度，我可以帮你看一下。
我先
就来看，也不是在参考，就是看有没有漏掉。就是多一个人帮你及时统计一下，是不是有什么漏？
因为我现在是就是以那个时间点先往前扣1个月。
对啊，有慢慢啦，对。
OK， 好，持续。
对，就是你到时候可以，如果想明显就可以的，你可以跟我，就你可以看一下你现在做出来的这个资料的样态，我可以看一下有没有什么问题。
我现在最大的坎应该就是在那个资料要先去做分析完，前面 introduction 跟那些分析结果都没有这个资料分析结果，其实写不下去。
前面的introduction，
你说其实可以稍微写，但是
当然啊，每个做研究其实introduction最后可以写，你要有答案才会结果才会去看这些，就是正常的，不用写。
我以为就是你要前言交代说这个政策或者什么之类的。
这种 background 你可以写，但是 introduction 通常到最后才会写。OK， 不过我可能到后面会讲一下怎么写的，就可以。
OK， 好，谢谢老师。
然后那个栏位跟那个，那你有确认吗？你有确认新的栏位在那儿？
那我以为是真的就是按有一些那个。
Okay, so let's continue. So before lecture, I would like to briefly discuss the homework 2, but I will also record a video to explain this. But here I just briefly explain. So homework 2 is also for the data practice, and you will have 4 big questions, and some questions are related to your, actually is for term paper. So for first question, I assume you might already know what's your research questions. So this question just kind of like, you can consider it's kind of like the writing for your term paper. What's your research questions? And what's your treatment variable? And what's your outcome? And you can use the potential outcome framework, try to define the causal effect you are interested in. So that is, you need to define what's your y1, y0, and the difference is the causal effect. And try to use this potential outcome framework, try to formulate the question you want to ask. So this is the first question. So this is not really related to the data. And the second question is about just help you to practice the command. So you will learn several commands from the video that I think is quite important for the data management. For example, the class. The class will help you to create the data from individual level to some aggregate level. This question just asks you to practice this command. So use class to create whatever data set, new data set, that might be useful for your analysis. So, but if your analysis actually does not really need to use this, you just create whatever data set is okay. Okay, but maybe sometimes you might need doing that. Okay, and then you briefly describe what is this new data set. So class will generate some new data set. So originally it's the individual level or firm level. Class can help you to become the aggregate level from like county year level, for example. And these might be useful for your analysis. Okay. And append is another command that can help you to append different year or different level data. So you will also create some new data set and just explain. And merge is help you to merge to get more variable from other data set. So you can use this to practice this command. And how to use this command, I just send you the video link. You can watch it. And third question is about how to draw the graph using this data, visualize the data. So use histogram to draw the display the variable you are interested in. It's help you to explore your data set for your term paper. And use the graph two-way to display the relationship between any two variables you are interested in. And you can choose the variable that you think is help you for your analysis. That is, this graph might be also be able to put in your term paper. So it's kind of also help you to do the term paper. And the final is do some preliminary analysis. You can just run the regression for your outcome and treatment. Just this, very simple, to see some correlation, positive or negative. But this regression almost have some omit variable bias, only if you use the data is from the randomized control trial. You don't need to control anything. But if you do not from this, your data is not from the randomized control trial, you might need to control something. So that means you will have omit variable bias. So this question is just discuss this omit variable bias, selection bias in the treatment group, treatment variable and the control outcome variable. So this just discuss. And also this is discuss. You will include some covariates, and you will discuss whether the covariates you include in your regression is not back control variable or not. Okay. So this is the homework 2, and the deadline is the May 9th. Okay, May 9th, before the May 9th, the class. Okay. So any questions for this? Okay. Okay. And I think that's my plan. I'm not sure. I will try to finish the synthetic control and regression discounted design. I think that's almost all the education strategy for the empirical analysis we can cover. And I hope I can teach this in the in-person class, because I think in-person class is more effective. It's better for learning. So I plan at most we might have at 1 or 2 more in-person class, and later we'll go online, because later just presentation, and this instrumental variable I will have the video, and also R is also will use the video, because I guess the situation will become worse. I guess. I'm not sure, but you can let me know any opinions. If you still prefer in-person class, I can also do like this. But I guess maybe we will have 1 or 2 in-person class. And I will try to finish the most important part, like synthetic control and regression discontinuity design. So that basically you learn almost all the useful identification strategies. Okay, so any question for this? That's my plan. But maybe the university will make some new announcement, we will just follow them. Like they cancel all the in-person class. All the class has to go online. So we will just follow. But if the university do not make such announcement, we might have the in-person class at most until the May 2nd. We try to finish all the important part based on the in-person class. Okay. And then just office hour and compulsory and presentation, and I can give you more office hour to help you to finish the term paper, to discuss the term paper. Okay, and the class will all become have the video. Okay, that's my plan. So any question for this? Okay. Okay, so synthetic control method is also a new method that are quite popular recently. And you can apply this for many situations. So it's similar to the difference. And it also helps you to evaluate the causal effect of the treatment. And there are several features. It can evaluate the treatment effect on aggregate outcome. Usually, it's used for the aggregate outcome. But it also can evaluate causal effect on the individual or household level outcome. But we seldom do that because the computational burden for the synthetic control method is very high. So the sample size cannot be very large, at least this moment. But maybe later, we have enough computational power, we can expand to the large sample size. But these methods especially useful if you want to look at the treatment effect on aggregate outcome. That means only one treated unit or very few treated units. For example, just one country get a treatment, one city get a treatment, and you want to know the effect of treatment on that city, on that country. You can consider using this method. And I think such situation actually happen a lot, so I think it's quite useful. And it's use the data-driven procedure to construct the control groups, the artificial control group. So I will show you what this means. So basically use very small number of non-treated units to build the suitable counterfactual to make you can do the causal inference. So what is this? The main idea is you use a long panel data to build the weight average of non-treated units and use this weight average outcome for the non-treated units to construct the so-called synthetic unit. And compare these synthetic units basically can best reproduce the characteristic of the treated unit over time during the pre-treatment period. And if you can construct these synthetic units, then you can get a causal effect of treatment by just simple difference in the post-treatment period between the treated unit and synthetic units. And I will use this example to demonstrate what this means. This is a very classical example when you do the synthetic control. They want to look at the policy happened in 1989. That is the anti-tobacco policy in California. It's a policy try to discourage people smoking. They impose some tax rate for the cigarette and also do a lot of campaign try to persuade people not to smoke, something like this. And it happened in 1989. And only in the California. And the outcome they want to look at is the cigarette consumption. Cigarette consumption. So in that case, maybe you want to use the difference. So the treatment group is California, and the control group is the rest of US. That is other states in US. But if you do that, you might find there's no common trend. So the solid line is California cigarette consumption. And the dashed line is the simple average of all the rest of US. Okay. And you can see these two group of people, their trend is very different. So you cannot say this difference after treatment happened. This difference cannot really represent the causal effect policy. Because before that, the California and the rest of US, their cigarette consumption already have some gap. And this gap sometimes is bigger, sometimes is smaller. There's no common trend. So if they have some gap, but the gap is constant over time, you still can use difference to estimate the causal effect. Because you just want to know whether the gap becomes larger or smaller after policy implement. But in this case, the treatment group and control group, they have some gap. And the gap is very time varying, very different over time. So in that case, you cannot use difference. Because difference just do simple average of all the control units. But you can use synthetic control. The synthetic control is not just use the simple average of the rest of US. They use the weight average of the state, the control state. So what is the weight average? Is the weight, they will give the weight, the higher weight to the state that are more similar to the California before treatment happened. For example, maybe New York, their cigarette consumption are very similar to the California before treatment happened. They will receive 50% weight. And Alaska also very similar. Utah also similar. So they also receive some weight. So they use this weight average to construct the synthetic California. And how they choose the weight is based on whether they can produce this similar trend, similar outcome as the California's outcome. So they choose the way to make the pre-treatment outcome are very similar to the treated unit. And if they can find such weight, so such weight could be 50% for New York, 30% for Alaska, 20% for Illinois, for example. So other states is not very similar to the California's, their pre-treatment outcome. They all receive 0. So, and then it might produce this synthetic California that can basically reproduce the pre-treatment outcome over time until the treatment happens. So if that, you can consider any difference between the real California and synthetic California. This difference can represent the causal effect of the policy. So that's the main idea of the synthetic control method. Okay. So any questions? And you can evaluate the policy impact for each year. For example, 1990, 1991, 1992 until 2000. Each gap between the California and this artificial California, synthetic California, is the effect for that policy. If there's no other policy also affect the cigarette consumption happen around this time period. Okay. You can do that. Okay. So synthetic control actually builds on the setting of the standard difference model, but makes following change. They have some disadvantage. The first advantage is we will use series data-driven approach to construct the control groups, the counterfactuals. Okay. And this data-driven procedure will reduce the manipulation of the choice of the control group. So now you just put all the US into the data, and the algorithm will directly help you to select who gets higher weight, who gets lower weight. Instead of the researcher can decide who become the control group or who do not. Okay. So it's more objective. Okay. Another thing is synthetic control can help you to control the allow for the time varying individual or group specific heterogeneity. And that's something we will discuss later. So compared to the difference, we can deal with this time varying effect from the individual or group level on observed factors. And that is the difference cannot do that. Okay. But the benefit of synthetic control method come with some cost. First is we only can, no one actually derive the formula for the synthetic control estimates. It's asymptotic theory. So that means we get some effects. We know there's some effect, but we don't know whether this estimate is significantly different from 0 or not, because we don't know this estimate its distribution. And also their standard error. So we cannot say know their t statistics and know the p-value for this estimate. No formula to let us know what's the distribution of this estimate, the synthetic control estimate. So no one actually derived, because this is a new method. It still need time to formalize their theory. So instead, we use permutation method to do statistical inference to compute the p-value. So we still can know whether our estimate is significantly different from 0 or not. We're using the permutation method. And what is this permutation method? We will discuss later. So basically, we will use a lot of placebo estimate to construct the distribution of synthetic control estimator and compare our real estimate with this based on the control group's estimate. We can get a p-value. Okay. And also the education assumption is somehow ambiguous. You can see later, actually there's now a lot of regulation on the synthetic control method. They kind of like a bit arbitrary. If you know a lot of regulation on this method. So enough guideline for this method. So the researcher actually do not know, will get very different result if you use another predictor. Later I will let you know. And also the computational time is far than the difference estimator, because we need to find a weight to construct a weight average. And finding the weight for each control groups is time consuming. Okay. So any questions for this?
前面两个是都只是因为现在还没发展，最近以后会是这样。
是，后面这个也是啊。如果有更好的电脑、超强的电脑，硬体跟上，应该也可以解决。对，就是这个还未知，因为这个方法大概是2010年才开始有被发展出来，所以它现在还不到，大概10年，不到20年。对，但是它可以用的地方还蛮广泛，因为它需要的资料不用很好，加总的资料就可以。那这个资料通常都是公开的，比较不会有什么个资的问题。Okay. So any other questions?
就是请问一下，前面计算它那个相似性，比如 California 那个，它是用在 treatment 之前资料去比对那个相似性，还是所有？
对对对 ，treatment 之前，待会我会给大家看一下那个它的 objective function 是什么，就是它是找一个 weight 去 minimize 这些 pre-treatment 的 characteristic 的 difference。
那为什么不能？就是它为什么不会是只是在 treatment 之前相似，它本身本质上在 treatment 之后，可能有一些随着时间而不会有差异。
treatment 之前相似，对对，它是让 treatment 之前。
它是那一段让它最相近，它会不会原本在 treatment 之后就是不相近？
哦。
treatment 的那段时间比较长。
对，这是好问题，有可能，但他假设没有这样的事情，这是假设，就是说，他假设是实验组跟对照组在 treatment 后的差别，就是因为这个政策，就只有这个政策产生这个额外的，就是说，所有其他干扰因素都被这个 pre-treatment 的 fitting 捕捉掉了，都已经抓掉了。在 treatment 发生后，没有额外多出一个新的干扰因素，除了这个 treatment 本身影响。如果有，当然就是你就开始分不清楚这个 gap 是从哪里来的。但是他得这样假设，不然他没办法讲下去。对，但他可以讲的是，treatment 发生以前的其他干扰因素，假设会延伸到后面。都会在这前面都被建构捕捉了，对，因为它等于是用synthetic California 抓掉了一些看不到的一些因素。
像不会像那些机器学习方法会有 overfitting 的问题吗？就是刚好那一段是最它的那个
overfitting 哦，
就是可以让它是最贴近，但其实在别段都不符合。
这个。但是，应该是说，你说的这个状况，它就是假设没有。对对对对，它就是有这样的假设。对，待会会看到我说，就是你讲的这个假设，它其实就是假设，那些 unobserved factors，不会在 treatment 之后又有一些新增这些 observed factors。Any other questions? Okay, so let me use the potential outcome framework to formalize this method. So again, we use the same framework to do that. So we use this classical example to demonstrate to go through the concept of synthetic control method. That is the same method, the same example as I just mentioned before. And this is the example for a single treated unit with multiple non-treated units. So here, only California receives the treatment, and other state does not receive. But maybe in the next class, we will extend this framework to the multiple treated units. Okay. And the background for this policy is in 1988, the California passed the anti-tobacco law. So basically, it increased the tax, cigarette tax, by $0.25 per pack, and also do a lot of anti-tobacco campaigns, and also establish some laws, cleaner air laws, something like this. So they want to know, how does this policy affect the cigarette consumption in California? Okay, so suppose the notation is like this. We have J units. So in this case, it's all the US states, right? 50 states or 40. I think they only use 40 states. So you can consider J plus 1 units 40 units. And we usually, is a panel data at aggregate level. Follow these units over time, from the year 1 to T year. And treatment happen in T0 plus 1. And only unit 1 get a treatment. So that is California, is 1. And unit 2 to unit j plus 1 is control unit. And pre-treatment period is the year 1 to T0. And post-treatment period is T0 plus 1 to T. Okay? And our goal is measure the causal effect of the treatment on the outcome for the treated unit 1 for the California. So that's the causal effect of the policy on California. That's the causal effect we get. So the treatment D equal to 1 means the units get a treatment during the post-treatment period. And D equal to 0 means the units always untreated, are always untreated. Okay. And the potential outcome now is Y1, and we also have the time dimension. So it's the unit 1 if they receive the treatment at time t. Y1 will be realized. And if not, Y0 will be realized. If this unit does not receive the treatment at time t, Y0 realized. And know that the unit in synthetic control methods is usually at aggregate level. Okay. So the observed outcome Y, before the treatment happen are always Y0 will be realized. Because both treated unit and untreated unit do not receive the treatment before treatment happen. And observed outcome Y after treatment happen, after T0 plus 1, it depends on treatment status. If you are treated units, Y1 realized. So California, the unit 1, Y1 realized. And other states, Y0 realized. Okay. So that is the notation. And the goal of this analysis, we try to know the causal effect of the treatment, the policy, on the treated unit 1, the outcome on the treated unit 1 over time. So we want to know the causal effect of the policy on cigarette consumption in California for the period 1990 until 2000, for example. So we want to know the effect for each year. So we use this alpha 1 to represent this factor over time. And the causal effect, basically ideally, is we want to know the unit 1's outcome if they get a treatment, and unit 1's outcome at time t if they do not receive the treatment. Their difference. But only Y1 is observed. Y0 we cannot observe. Because for unit 1, this is treated unit 1. At the time t, after treatment happened, this is treatment occur timing. After treatment happened, only Y1 is observed. Y0 is unobserved. So we want to use the synthetic control method to construct this Y0 unobserved counterfactual to get the causal effect for each year. Okay. So the following question is how to use observed data to construct this Y0. Okay. So there's some assumptions for the synthetic control. We basically assume the potential outcome if the unit 1 or unit I does not receive the treatment, the Y0 is determined by the following components. So Y0, this Y0 is constructed by this, kind of like assumption for this synthetic control. One component is time effect. That's we can control just over time. And some is Z, is observed pre-treatment covariates. For example, for cigarette consumption in California, maybe you want to find the state with very similar population size as California, or the share of young people similar to the California. That could be the Z. That's something observed characteristics of the unit. That's something not very easy to control because this is observed. And the key thing is mu I. So mu I is the permanent unobserved variable. Something unobserved. So we are not be able to control it. And that's why we need to use synthetic control, because the method we can deal with this. And we also allow this unobserved factor has some time varying effect, delta t. So the mu i's effect is time varying. That means it will change over time. So synthetic control allows this time varying response of the unobserved factors. So in the difference in difference, we does not allow this. In the difference in difference, the y0 is looked like this. Y0 is delta t z and mu I. In difference, we does not allow a time effect. I mean, the time effect is the constant. We only have the group. We only can get the effect of the group specific effect. But we do not allow this group effect has some time varying effect on the outcomes. So the synthetic control method can deal with this effect, this issue. Okay. So how can they deal with this issue? I will let you know later. But this kind of assume the number of unobserved factors are fixed over time, fixed over the time period. So this does not allow structure breaks. That means this does not allow after treatment happen, we have more unobserved factor suddenly show up. If we cannot estimate. So we kind of assume there's no such, the number of unobserved factors is fixed over time. So we just fit the pre-treatment period's outcome that can help us to capture all unobserved factors. So it's kind of your questions. Okay. So we assume like this. So based on this assumption, we can do the estimation. So the synthetic control method, as I say, the goal is we try to construct the Y0 counterfactual for the treated unit 1 for the California. And synthetic control method suggests the treatment effect can be estimated by using, we can replace this unobserved Y0 with this. This is what? This is the weight average over other states. They are observed outcomes. And how to choose the weight is the key. We want to choose the weight that can reproduce the outcome before treatment happened for the treated unit 1 and other characteristics also. So how we choose the weight? We choose the weight, so each state, each unit will receive some weight, and the weight between 0 to 1. So some state just 0 because their characteristics are very different from California. And some state receive very high weight because they are similar to California. So each state will allocate some weight. And how to choose the weight is we try to minimize the difference in the pretreatment characteristics X between the treated unit and non-treated units. So basically, we want to minimize this. This is the distance between the treated unit 1's, their pretreatment characteristics, including what's the pretreatment characteristics, including observed characteristics Z, I just mentioned. Population size of some state, or the share of young people. We try to make these characteristics are similar to California, the treated unit 1. We try to find some weight to minimize their difference. And the X also include the pre-treatment outcome. That is the outcome in the beginning until the period right before treatment happened, the YT0. After T0, time T0, treatment happened. So we want to minimize the difference for each time period of the non-treated unit and treated unit by choosing the weight. So, and also we also have some regulation. That is, the sum of the weight need to be 1, cannot bigger than 1. So that means the weight need to be positive but cannot become more than 1. Okay. So in that case, so the different weight, you can imagine different weights will give you different synthetic control units. Okay. So if you put different characteristics, that will give you different weight and different synthetic control units, and also different causal effect. So they kind of like does not, if you put different things, you might get different result. But so you can do several robustness check. That is, you cannot change dramatically from a positive effect to the negative effect by just change a little bit of your observed characteristics. Okay. And you will all use all the pre-treatment outcome to match the fitting. Okay. So ideally, we want to choose the weight. Try to match the unit 1's observed characteristics. So based on the assumption we just mentioned, we want to construct the Y0 using the weight average of the control group's outcome. So the goal is we want to match their component. One component is Z, another component is mu I. One is observed, another is unobserved. So our goal is try to find a way to match the Z, the control group's weight average to match the treated unit Z1. And unobserved characteristic weight average to match unobserved characteristic of the treated unit 1. But mu I is unobserved. That's the problem. And the beauty and the solution of a synthetic control method is we don't match the mu I. We don't try to fit the mu I. We fit the pre-treatment outcome is enough. We fit every year's pre-treatment outcome for the treated unit 1, every year. If we can find a way to match the time pass of the outcome before treatment happened for the treated unit 1, for the California, it automatically match the mu. Because if you can match the outcome, it's kind of match the Y0 over time before treatment happened. If you can do that, that means you already match the unobserved thing. Otherwise, you cannot match this. You kind of like match the Y0 because the treatment, before pre-treatment period, Y0 realized. So you kind of like use the weight average of non-treated unit to match the treated unit's pre-treatment outcomes. If you can find such weight help you to match this every year before treatment happen, you kind of like match the mu unobserved things. So that's the solution. That's why we match these pre-treatment outcomes. Okay. So here is the theorem. Is suppose we find a weight that can help us to match the treated unit 1 all the outcome before treatment happened. If we can find a weight to do that and match the treated unit 1 its observed characteristics. So given this, if we can find a way to do that, given that, then we can claim this is true. That is, after treatment happened, T bigger than T0 is after treatment happened. the Y0 for the treated unit 1, the difference between this weight average of observed outcome using the control group, the weighting average of the observed outcome, these two differences will converge to a 0. That means if this is true, we can use this weight average of observed outcome for using non-treated unit to replace something unobserved, the Y0 for the treated unit 1. That is, what if California does not implement the policy? What's the outcome with that? We can use other states' weight average outcome to replace Y0 because they are very close. And this need this condition. And also another condition is as T0 go to infinity. So that means this is pre-treatment period. The pre-treatment period need to be long, very long. If we can match very long pre-treatment period, that means we kind of capture the key unobserved characteristics over time and also observed characteristics. Then we can safely use this weight average, the synthetic unit, to replace the treated unit, its unobserved outcome. That is the treated unit, the potential outcome without treatment for the treated unit 1. Okay. So any questions? So basically it's just say, if we can find the weight average that can help us to construct the synthetic California that can match every years in the outcome before treatment happen, if we can find such weight, then we can use this weight average to replace Y0. So basically it say we can just use this instead of using Y0. So Y1 is being realized. Y1 for treated unit 1, Y1 realized. But we don't know Y0. But the above theory say if we can find a weight that can match the pre-treatment period's outcome and observe characteristics, if we can have this weight, we can use this weighting average to replace Y0. And then we can get a causal effect. Just compare this and this. We can get a causal effect for each period. Okay. Okay, so any question for this? Okay. Okay, so yeah, so time's up. So next I will, so actually also go, actually it's right timing to stop here. So next I would like to let you know how to do the statistical inference hypothesis testing using the permutation method, and also how to use Stata to implement this method. Okay, so any questions? Okay, so hopefully we can still have the in-person class next week, but feel free if you don't want to come to the class, if you have any safety concern, because I will record the video, but I just record the screen. So I don't know whether the quality is good or not. Okay. Okay, so that's all for today's class.